All right, so this problem is a rather tricky circular motion question because it involves both circular motion and inclines. So you have to be very careful on the vector components and the free body diagrams you draw to solve it successfully. So first, we have a car going around a highway curve. We're told the radius that the curve is, and we're told the angle that it's banked at. And our first question is to determine the vehicle speed for which this curve will work if there is no friction at all. In other words, how fast can you possibly go and make it around this curve without sliding up or down? And there's no free body diagram requirement, but that's usually a good place to start. So I'm going to draw that. All right, so there's our slope, and there's our car, and now we draw in the forces. Right, there's the weight of the car, there's the normal force, and because there's no friction, that's it. Right, those are the only forces. The next step is we have to think about how we're going to turn this into a solvable problem. Right, because if this was not a circular motion question, our coordinate system would, let's not do that. Our coordinate system would look like this, right? Parallel to the incline and perpendicular to the incline. That's what we typically do. But circular motion requires us to identify forces that point towards the center of the circle, which is that green direction. And our blue coordinate system is none of that, right? It doesn't work. So we have to do things a little bit differently. So now I'm going to clear out some of what I just did. So the blue stuff is not what we're going to do because it won't work for this problem. We can certainly talk about the components like that, but it doesn't help us because we need components. Actually, let's do it dotted. Right, we need components that point towards the center of the circle, so we have to have the green coordinate system instead, which is a bit different than what you're used to for most inclined plane problems. So, we draw a coordinate system like that. We see that the weight is entirely in the up and down direction, so we're fine. But the normal force has two components, right? One of those components points towards the center of the circle, and one of those components balances the weight. So we can write Newton's laws in 2 dimensions. I'm going to use x and y, because that's more or less what it is, but the x direction is also the towards the center of the circle direction on how I've drawn it. So x, net force equals ma, y, net force equals ma. So now we identify what motions we have in each direction. So because the x direction is the towards the center of the circle direction, we have a centripetal acceleration there. And we see that we have, if I use green, right, that is 15 degrees, the angle of the incline, right, same thing. So this component that points towards the center of the circle is the opposite side, so n sine theta, and that's the only force in that direction, is mv squared over r. And so your instinct might be, oh, normal force, that must be equal to the weight. But it's not. Right, our free body diagram shows that the weight is only being balanced by part of the normal force. That's what we're going to use this direction to find. So we have the other component of the normal force that points up, and the weight that points down, and we want it to, right, this is the speed that's appropriate. So this car is not sliding up or down the incline. In other words, it's staying stationary in that vertical direction. So that equals 0, not accelerating in that direction. So we can solve that the normal force is actually going to be mg over cosine theta. And then this can get substituted in, so mg over cosine theta times sine theta is mv squared over r. And now you can see a couple, hopefully, fast simplifications, right? The mass cancels, and sine over cosine is tangent, so g tangent theta is v squared over r. And now we're asked to solve for what is the speed, so we're going to solve for v, which I'll do over here. So v is the square root of gr tangent theta. And we're given all the numbers, right? So we can actually determine the speed, right? G is 9.8, r is the 100-meter radius, and tangent theta is tangent of 15 degrees. You plug that all into your calculator, you'll get 16.2 meters per second. So that's our answer. All right, so that's part A, no friction. Parts B and C will involve friction, which makes things a good bit more complicated, but the approach is going to be the same. That's, I think, why they gave part A with no friction, because we're not going to change how we approach the problem, just the math is going to get a little bit uglier. So, part B, we're asked to draw a free body diagram, right, for when there's friction present. We're told that the car is able to make the turn at 25 meters per second when there is friction. So I'll redraw my incline, and some things don't change, right? Just because there's friction, it doesn't affect the normal force or the weight. So the question to figure out with friction is which direction does it point, right? Because it could point this way, or it could point that way, right? If the car wants to slide up the incline, then friction would oppose that and point down. If the car wants to slide down the incline, then friction would oppose that and point up. And you might be thinking, well, how do we know what the car is trying to do? And that's sort of hidden in the information that we're told that it's able to do that turn at 25 meters per second. Without friction, it was going slower, right? Our previous answer says without friction, we could only do it at 16 meters per second. With friction, we can go faster. That means if we didn't have friction and we went at 25 meters per second, the car would slide that way, right? It's going too fast without friction. So, because the car wants to slide up at that higher speed, we now know what direction friction must be in. It has to point down the incline. And specifically, it has to be static friction, right? That, again, we don't want the car to slip. It stays sort of where it's at vertically on the incline. So that's the only thing that's changed, right? We've added the static friction force, parallel to the incline pointing down. Now it's kind of back to the same from part A. We have to use a coordinate system that gives us a force that points towards the center of the circle. And that means the same coordinate system we had before. And once again, we have the x, or the towards the center of the circle direction, and the y, or the vertical part. So we can see that the normal force, again, doesn't change. And friction also is going to have two components. So in the x direction, we still have n sine theta. I should draw, right? That's theta. And that is also, those are the same theta angles, right? All three of those. So we have n sine theta still, but now we have a second force that points towards the center of the circle, right? They're both pointing in the same direction, so I'll give it a positive towards the center. And part of friction also points there. And this is the part that's adjacent to the angle, so this is going to be cosine theta. And that equals ma. Right, because this one we know it has an acceleration. It's going in a circle. In the vertical direction, once again, normal force is not any different. Weight down, not any different. But now again, we have a new bit. We have part of friction that actually points downward. This is a very easy force to miss. You don't think about friction sort of helping balance a weight or something like that. But based on the coordinate system we picked, there is a component of friction that points down, so we have to include it. Right? It's the sine component. And that is 0, right? So we don't want it to slide up or down. So as you can see, it's not a huge amount different, but it's a little bit more complicated. So, first thing I do, I remember that the x acceleration is centripetal, so I can replace a with v squared over r. So I'm just going to erase and do rather than rewrite. And so now we're asked to solve for the coefficient of friction, in fact, the minimum coefficient of friction. So the minimum coefficient of friction is given when the static friction force, right, in general, oops, I just wrote it wrong. right? The static friction force is less than or equal to the coefficient of static friction times the normal force. So, to get the maximum force for a given coefficient of friction, we need to make this an equality, the maximum amount of friction for a given coefficient. So Fs is equal to mu s min times n, right? That gives us the maximum amount of friction for the given coefficient. So we can substitute that in, now that we know what our friction force looks like. And sine theta, that doesn't change. I'm just going to write mu s rather than mu s min, just for simplicity. Okay. And so once again, we're at the same spot where it would be nice and easy if we could just substitute in the normal force equals the weight and then like solve that one. But the normal force is not equal to the weight, right? For the same reasoning as before. We have to be a little bit more careful, right? We have two unknowns, but they're very tricky in how they're mixed together. Two equations and new ones. It can be solved. We have to be a little careful. So how you do this is kind of up to you. The approach I used was to solve this vertical part for the normal force. So I'm going to do that, right? I'll move mg to the other side of the equation and factor out an n. Right, so now we can see that the normal force is mg over a complicated expression. Right, and we can take this and we can put it in up there. And now we'll have one equation that only has mu s in it. Right, so I'm going to go to another page for that because the algebra is going to get a little ugly. So, actually, yeah. Okay, so the first term turns into mg over that whole denominator and then there's a sine theta left over, right? It was n sine theta was the first term. That's that. The second term, mu s mg cosine theta, right? It was mu s n cosine theta originally, and then we have that whole denominator mess there. And that equals mv squared over r. Okay, so first good thing, we can now get rid of the masses, right? There's one of those in each term. So we are trying to solve for mu s, which appears here, here, and here. So this is not, we still have a lot of algebra to do. We have to get rid of the denominator. So I'm going to multiply both sides by this thing in red. Right, multiply both sides by that. So we're left with g sine theta plus mu s g cosine theta. Oh, I'm also going to multiply both sides by r to get rid of the denominators entirely. Actually, let me rewrite that from scratch then. Yeah, so gr sine theta plus mu s gr cosine theta equals v squared cosine. Actually, I'm also gonna distribute the v squared, so we'll have v squared cosine theta minus v squared mu s sine theta. So we're making progress. Now I'm going to put everything that has a mu s on one side of the equation by adding the v squared mu s term, and everything that doesn't have a mu s on the other side of the equation. So mu s gr cosine theta plus v squared mu s sine theta equals v squared cosine theta minus gr sine theta. And now I can factor out a mu s and divide by what's left over. So mu s equals v squared cosine theta minus gr sine theta. And we have left over a v squared sine theta and a gr cosine theta. Right? And so that's our algebraic solution. Now we have to be very careful, right? We know all these values, right? We have v is 25, theta is 15, r is 100, and g is still 9.8. So you can plug that into your calculator. You have to be very careful with parentheses, but you should do that. You have enough to get the numerical answer. And so if you do that, I'll put the minimum back in. You get that as your answer, 0.32. A lot of algebra in that problem. But parts A and B are definitely ones you should be able to do, and you should be able to set up part C very, very safely at this point.